Okay, you've definitely heard this phrase before, right? In movies, in books, on TV, this idea that one tiny little action can change the entire world. We call it the butterfly effect. But here's the crazy part. What we think it means, it's pretty much the exact opposite of what the scientist who came up with it was actually trying to say. So yeah, let's get into it.
And this is where it all began. This one question from a meteorologist named Edward Lorenz back in 1972. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? I mean, it sounds so dramatic, right? It totally captured everyone's imagination. But the answer he was getting at, well, it's way more interesting than a simple yes or no.
So, before we get to the real science, let's talk about the story we're all familiar with. You know, the one we see in all the sci-fi movies.
Yeah, the pop culture version is usually something like this. A character goes back in time, accidentally steps on a bug, and when they come back, the future is completely different in some huge specific way. It's this clean, straight line from cause to effect. A leads directly to B. Super simple, right? Well, not exactly.
And this really breaks down the confusion. On one side, you've got the movie idea. This neat, tidy chain reaction. One butterfly flap, one tornado. Predictable. But on the other side is the real science idea, which is the total opposite. It's about a future that's so sensitive to tiny changes that it becomes completely, fundamentally unpredictable. And this is the big twist. Lorenz wasn't saying we could trace a tornado back to one specific butterfly. He was saying we can't do that, ever. His discovery was really about a fundamental limit to what we can possibly know. And it didn't start with a butterfly at all. Nope, it started with a computer.
All right, so the true origin story isn't some big, dramatic moment. It's actually a super quiet, totally accidental discovery in a computer lab way back in the early 1960s.
So our main guy here is Edward Lorenz. He's a meteorologist over at MIT, and he's working on the holy grail of his field, trying to build a computer model that can predict the weather way, way out into the future.
Okay, so one day he wants to run a simulation again. Now these old computers were slow. So to save some time, he decided to take a little shortcut. Instead of starting the whole thing from scratch, he just typed in the numbers from an earlier printout to pick up where he left off.
He glances at his printout, finds the number he needs, let's say it's for air currents, and types it in. The number is 0.506. Easy.
But, and this is the key detail, the computer wasn't just storing 0.506. Internally, it was holding the number with way more precision. 0.506127. I mean, the difference is minuscule, right? A tiny rounding error. You'd think it wouldn't matter at all. So Lorenz goes off to get a coffee or whatever, and when he comes back an hour later, he expects the new simulation to look exactly like the old one. But it didn't. At first, the two graphs were really close, but then they started to drift apart, and pretty soon the two weather forecasts were completely different, like not even close. That tiny, almost non-existent difference in the starting number had led to a massive change in the outcome. And right there, that was basically the birth of chaos theory.
So that little rounding error, it wasn't just a bug in the machine. It turned out to be a peek into a whole new kind of science, a science that's all about unpredictability.
The official sciencey name for this is sensitive dependence on initial conditions, or SDIC for short. That's a mouthful, but it's really the proper name for the butterfly effect. And all it means is that in some systems, a super small, almost unmeasurable change at the very beginning can blow up into huge, completely different results down the line.
So what makes a system chaotic like this? Well, you basically need two ingredients. First, the system has to be nonlinear, which just means that cause and effect aren't nicely proportional. A small push doesn't always lead to a small result. And second, the system has to mix things up. A great analogy is kneading dough. You stretch it, which pulls things apart, and then you fold it back on itself, bringing things that were far apart close together. That constant stretching and folding is what makes those tiny initial differences grow and grow.
If you want a really cool, real-world example, look no further than a double-rod pendulum. A normal single pendulum, totally predictable. But you add that second arm, and it goes completely wild. It becomes chaotic. If you set up two of them and release them from what looks like the exact same spot, within just a few seconds, they'll be swinging in completely different, unpredictable patterns.
What's really cool is that Lorenz didn't just figure this out mathematically. He actually found a way to draw it, to create a picture of what chaos looks like. So what he did was he took his super complex weather model and simplified it way, way down to just three key variables. You've got the rate of airflow, the horizontal temperature, and the vertical temperature. Then, he told his computer to plot these three things on a graph as they changed over time. As the program ran, it started tracing a path, drawing a shape in 3D space that represented the state of his simplified weather system. And the shape that appeared is what we now call the Lorenz Attractor. And here's the best part, in this amazing bit of scientific coincidence, the picture that the math drew looked just like a butterfly.
This kind of shape has a special name, a strange attractor. It's an attractor because no matter where the system starts, its path is always pulled towards this general shape. And it's strange because the line that's being drawn, well, it never repeats its exact path. It also never crosses itself. It's just this infinitely long, complex line, all folded up into a finite space.
Okay, so now that we have all that background, let's circle back and nail down what the real butterfly effect actually means. The most important thing to get is how different this is from a simple chain reaction. Like, a domino effect is totally predictable. A leads to B leads to C. Easy. But the real butterfly effect is nonlinear and systemic. The whole point, the defining feature of the discovery, is that the final outcome is completely and totally unpredictable.
And that right there is the true meaning of it all. The butterfly effect isn't some empowering story about how one little action can change the world in a predictable way. It's a lesson in humility. It's telling us that for really complex systems, like the weather, or the stock market, or an ecosystem, our ability to see the future is limited. Not because our computers are too slow, but because that unpredictability is baked right into the nature of the system itself.
So in the end, it was never really about the power of one butterfly. It's about living in a world that is so deeply interconnected that everything, every tiny, unmeasurable little thing, is part of a future that we can never ever fully predict. It's the flap of every butterfly, the warmth from every single light bulb, all of it feeding into a future that follows rules but is still forever beyond our grasp. And that thought really changes how you look at the world, doesn't it? It's not some simple machine we can figure out. It's something way more complex, and honestly, way more mysterious.